morning. This will be the concluding lecture in this course on an introduction to explosions and explosion safety. As we discussed during the earlier 38 to 39 lectures, something on what constitutes an explosion, what are the different types of explosions, and also how to model the different types of explosions, be it a gaseous vapor mixture in confined unconfined geometry, be it a solid explosive, be it a liquid explosion, be it something like a physical explosion. We looked at the modeling of the explosion and also determined what are the consequences, what are the damage, what is the type of blast wave, what is the type of overpressure, what is the type of impulse what you get from an explosion, namely the consequences. And by now we are very clear about explosions in general, and also we talked of inerting vents and all that to bring down the destructive nature of the explosions. And having said that, we also in the last lecture looked at quantification of damages from explosion, quantification of damages. We looked at the dose response curves, we looked at the probit, and now we are in a position to say, well, an explosion is something undesirable and an explosive. It could be a gas, it could be a liquid, it could be a mixture, it could be anything. It must be handled with care. That means the storage of the explosive, maybe the transport of the explosive, also maybe the generation of the explosive plus storage plus transport plus the actual use, that is in application, must be done with some safety precautions in mind. But whatever be the type of safety criterion we use, accidents do happen. Like for instance, I am very careful to cross the road, I am very fearful of the traffic, I take all precautions, still somebody can come and hit me and I could still get hurt. Therefore, accidents are something which are unplanned activity. Being unplanned, I think it is necessary to see under what conditions accidents can take place and also ensure that these accidents in the use of explosives do not generally occur. Therefore, let us get into some little more details of accidents. When we say an unplanned activity is an accident, and there is always a risk involved in whatever we do, and there is a greater risk in use of explosives. Therefore, if there is a risk, can you evaluate or identify the risk? Like for instance, identify what is the probability with which an explosion can take place in a given set of conditions, and if we are very clear about it, then maybe we can take some steps to counteract the occurrence of these explosions. Having said risk, and having said something about accidents, there is always a chance that an accident will occur. When I say chance, what is it I mean? Well, there is a possibility, and when we say chance in Arabic, the word chance is known as azar, and therefore we say a substance is hazardous. From the word hazar, you say hazardous, and when we say hazardous substances, we say, well, explosives are hazardous substances and have to be handled with care. When we say hazard, we mean further potential for an accident to take place. That means we need to reduce the potential, and that is where we see all substances like liquid fuels, when they are being transported, they say hazardous substance, please be careful, and in case there is a spill, maybe you could form an explosive substance. Therefore, we talk in terms of hazardous substances, and potential for an accident to take place is always there, and that is the meaning of the word hazard. And when we talk in terms of risk, well, the risk should be so small, that means the chances of an accident to take place must be so small that maybe we should be able to ensure that an accident involving these explosives do not take place, and that is why we do the risk analysis. Having said this, let us also take a look, what is it we are looking for? we say we cannot zero the or make the chance of having an accident to be 0. Therefore, all what we can say is make it as low as practically possible or as low as reasonably possible, or we call it as ALARP. This is the word we use, namely we would like the risk to be as low as reasonably possible, and let us work towards this. And in this class today, we will do we will work on the subject of risk analysis of the hazardous substances, namely explosive. There are different types of doing a risk analysis. For instance, you have methods like risk analysis. Maybe you have to be able to identify the potential for causing an accident, let us say identify the hazard. We also need to be able to carry out the precise quantification of risk in the risk analysis. We should be also able to do what are the consequences if you do have an accident, and therefore, maybe the analysis of the consequence has to be done. And we must also not forget, if an accident can occur more frequently, well, it leads to more chances of an accident taking place. Something like a frequency analysis has to be done. And there are different ways of quantifying all this, and the types of risk analysis which are done are something like, we say, you say what if analysis. Is something simple. What if a spill occurs? Will it explode? Under what conditions will it explode? Maybe I could use this, but it is not very quantitative though. I could also talk in terms of something like second, maybe a safety audit or a safety check, in which case maybe I make sure that all the safety procedures are built in, but again the safety audit cannot really quantify the type of risk involved. I want to find out what is the probability of having a risk. Maybe the third could be, we can talk in terms of failure modes, effects, and criticality analysis. This is known as FMECA, failure modes, effects, and criticality analysis. But these three cannot directly give you what is the type of the quantification of the risk involved. They are necessary because it helps you to understand what are the reasons for the explosion, what are the safety features which need to be followed, also the different failure modes, effects, and criticality analysis can come out with something like standard deviations and the type of probability of an explosion. But what I do is, I do something which is a little bit different. In the class today, I do three types of risk analysis only. Let us say fault tree analysis, the second one which I do is event tree analysis, and the third what I do is known as HAZOP, hazards and operability analysis. These are the three, and maybe in the two we will be able to identify the risk involved and also identify in the process, looking at the tree diagram, what are the type of hazards and what type of hazards constitute most to having an explosion. While in HAZOP, we will be basically looking at the consequence analysis and frequency analysis and coming out with suggestions on having a plant operate under conditions under which the risk is as low as reasonably possible. Having introduced the subject, let us go to the fault tree type of analysis. In this, what is done is we look at something like a deductive logic, namely the final scenario what you have is an explosion taking place. Let us say that the final event is an explosion. We start from the final event. Let us say this is the final event, which is an explosion. We try to identify the faults or the precursor events which ultimately lead to this explosion. Like for instance, maybe this explosion could have risen out of some fault over here. Some may be mismanagement, some mishandling, maybe an ignition source coming in contact with the fuel which it should not have done. Maybe this fault could have come from some other fault, let us say F1 and F2. Maybe these faults could have come from something like F3 fault and F4 fault or some more basic events, and so on. This could have come from F5 and F6. Maybe these things could have come like this. Therefore, we start from the final event and keep working out what are the basic faults which could result in this particular explosion. Point 1. Point 2, when we look at the basic events, we can also say a basic event I can always say from generalities, like it occurs in nature so many times. I can put a probability to the basic event and work out the probability of each of the intermediate faults or intermediate events which are taking place and arrive at the final probability of an explosion. Therefore, you have something like branching out, like something like a tree branching out, and it is known, this diagram is known as a fault tree. Having said that, the events which are ultimately the last set of events which cannot be broken down any further are known as basic events, and the intermediate faults are known as intermediate events. And now the basic events lead to an intermediate event. This intermediate event and this may be a basic event could lead to an intermediate event. This intermediate event and some other intermediate event leads to some other intermediate event, and this finally leads to an explosion, let us say. Maybe I could have another chain coming over here, maybe another fault over here, another fault over here, and therefore you have a tree. And therefore, you work out using deductive logic going from the final event to the basic events. Let's illustrate it through an example. Namely, let's say I have, let's say, a fire. And what happens in a fire? Well, I need a fuel, I need air, maybe both have to mix. I also need an ignition source. And therefore, if I say I want to create, my fire is my final goal, or this is my final event is a fire. And let's say my base or the basic events what I have are, let's say, a fuel and air which are mixed, which is available to me, which is basic. I also have something like an ignition source over here. Well, these two lead to my final event of a fire. But how do these two basic events relate to this? That means there has to be an opening for it to communicate with each other. Therefore, the basic events and also the intermediate events communicating with the next intermediate event, these intermediate events communicating with the final event is through gates. Like for instance, we enter a house through a gate, so also gate is an opening, and the basic events are communicated to the next set of events through gates or openings. There are different types of gates which are possible, and that is what makes this particular method essentially very challenging and fruitful. There are three types of gates possible. One is, we can talk in terms of an AND gate, we can talk in terms of an OR gate, we can also talk in terms of a gate which has some conditions imposed on it, like for instance, we can talk in terms of a conditional gate. What do we mean by these three gates or opening by which the basic events gets into the final event? Let's say I have fire. To have a fire, I go back to this particular example. Maybe I have a basic event in which my gas mixture is available, I have the basic event in which the ignition energy is available, and I am talking in terms of event in which I have a fire taking place. You know, to be able to form a fire, we talk in terms of a fire triangle or an explosion triangle, we need all the three together. We need the gas, we need this, then only I can result in a fire. Therefore, we say both of these things are required in the opening to be able to form a fire, and this AND gate is represented by something like an ellipse with a curve like this. This is what specifies an AND gate. Therefore, we have something like an AND gate. We also have something like an OR gate. OR gate means, supposing I want to form a cloud of explosive, or I am able to form it, and the different ways in which this cloud could have been formed are, maybe there is a tank, an LNG tank. In the LNG tank, I have the vent valve which gets opened, and well, the LNG rushes out, mixes with this and forms a cloud. Therefore, one of the basic event I can talk is, maybe the vent valve has by mistake opened. I could also think of a situation wherein somebody tampers with some of the check valves over here and allows the gas to pass through. So that means somebody tampers with your tank and allows the gas to come. And my final event I am talking is formation of a cloud. Therefore, my final event is, let us say, cloud formation of a combustible cloud. Now, I find if the vent valve by itself opens, well, I could release the gas and I could have a cloud being formed mixing with air. If somebody comes and tampers with it, also it releases. Therefore, how is this going to get communicated with the vent valve? How is it going to get communicated with the tampering thing, which is a basic event? It could be either one of them can result in the formation of a cloud, and this, which is either or, is what is the OR gate, and this OR gate is shown in the form of a fish. This is an OR gate. That means either one of them can do the job. The third type of gate, which we call is a conditional gate, is one in which maybe I have an event over here and I have the final event over here. This is the final event, and before this, maybe unless the pressure exceeds some limit, well, I cannot have the final event taking place, and therefore there is some condition associated, or rather we say, well, some condition is associated for the final to go through, and this particular gate is represented by a condition under which the intermediate event or the basic event can go to the final. That means this is the intermediate case. That means the pressure must exceed some limit, temperature must exceed, or concentration must exceed. This will be the condition, and this is known as the conditional gate. We use all these three gates to be able to draw back the diagram of the fault tree diagram, which I just now said. But in practice, the conditional gates are not that much used, and we will talk in terms of the AND gate and OR gate, but we do recognize the final the conditional gate would also be similar in application. Now, before I come back to the fault tree diagram, let us see what is the distinction between an AND gate in which both are required to form the event, in which case one of the two events can lead to the formation of the event. Therefore, how will I look at it? Let us say that the probability of an event, that is a gas mixture being formed, is P1. The probability of an ignition energy being available is, let us say, P2. Now, the final probability of forming a fire is equal to, has to be less than this probability and less than this probability, because both are to be equal, and therefore P is equal to P1 into P2 over here. In case the formation of the gas mixture is related to the energy requirements, which is not possible, but in case, let us say, one of the events, basic events, is related to this event here, Well, the probability will be greater than P1 into P2. In case of an AND gate, what is going to happen? Well, let us say that the probability of forming the vent valve opening is P1, somebody tampering with this is P2, this can independently give rise to this can independently give rise to this. Therefore, probability of forming this event is equal to P1 plus P2, this is the probability. And in case this is related to this, maybe while tampering the vent valve automatically opens or something, then in this case the probability of getting the final event based on these two events is less than P1 plus P2. Normally, the events are so chosen that they are independent of each other, and the probability is given by P1 in P2 in case of an AND gate and P1 plus P2 in case of an OR gate. Well, this is about it. Let us now go back and try to form a fault tree and try to calculate the probability of an explosion. Let's try to do it through an example, and the example which I take is maybe forming an explosion from, let us say, a spill at home. Let us assume I have a kitchen. Being a winter month, let us say that the doors and windows are all closed. In the kitchen, I have a cylinder, a gas cylinder, and the gas cylinder we know contains essentially butane C4H10. You have a pressure regulator, you have a rubber hose connecting to my stove over here, and the stove essentially consists of burner heads, and you have control valves over here. Therefore, this is the way I light a stove. It is quite possible, let us put down some clauses, it is quite possible that maybe the person using the kitchen forgot to close a valve, to close the valve of the stove. With the result, maybe the gas comes and into the kitchen which is locked, which is closed, windows are all closed, doors are closed. Maybe in the particular volume of the kitchen, I have, let us say, I form a gas mixture. What is this gas mixture? Maybe the butane air gas mixture. Scenario 1. Scenario 2, you have these cylinders which are recycled all the time. It is quite possible that the regulator of this gas cylinder is so old, maybe the person who supplies it gives me a defective regulator, and the regulator leaks, and this regulator leaks, and I could also form a cloud in the kitchen coming from the regulator leak. These are the two sources of the leakage, and well, these two sources of leakage form a cloud of butane air mixture in my kitchen, and as usual, people do not observe it. Well, the man in the house, he is used to smoking, he smokes a cigarette while coming into the kitchen. Therefore, the ignition source or energy source could be his cigarette burning, or the children in the house, they just come and they find some smelling kitchen, something is there in the kitchen. They try to put on a switch, and the spark from the switch or the electrical switch can result, and electrically the spark from the switch can cause the gas mixture to ignite and it explodes. Therefore, we say, well, in this particular example, you have an explosion taking place, and the explosion could come either from a gas cloud which is formed either from a valve which was left open unintentionally. You also see a regulator can cause this. These two are basic events. Formation of a cloud is an intermediate event. Similarly, I could also have something like an ignition source which is an intermediate event, and this ignition energy could come either of the basic events, like for instance a cigarette burning, the man smoking, or let us say a child comes and puts on a switch and releases some energy. Therefore, these four are the basic events. These two, formation of a cloud and this ignition energy, are the intermediate events, and these two intermediate events feed into the explosion. How they feed? They have to feed through the gates over here, I have a gate over here. What should these gates be? Let's now plot it in terms of the gates. We say this or this can lead to this, because either the valve opening or a regulator can lead to this cloud. Therefore, I will have something like a gate like this over here. I will have either the smoker who has the ignition energy because his cigarette is running hot, it can start a fire, or it can start the explosion, or the electrical spark can start an explosion. I have something like an OR gate over here, leads to the intermediate event, and I find, well, now I am left with this intermediate wherein a cloud of the gaseous mixture is formed. I also have ignition. Well, to form an explosion, I need both a fuel triangle, fuel and oxidizer, which is formed over here. I have the ignition source over here. This is also required. Therefore, I have an AND gate over here. And therefore, if I have to draw the fault tree diagram for this, I will have the following. I have, let's say the final event is the explosion in the kitchen. Well, I go through it through the AND gate, and the AND gate comes from two intermediate events. The intermediate events are having a combustible mixture or cloud, one having the energy for ignition, how did the combustible cloud got formed? Through the OR gate, I have either the basic event of maybe a valve of the stove being left open, or maybe a pressure regulator being faulty pressure regulator. Similarly, I have another OR gate over here. And what are the two basic events coming over here? One is maybe somebody smoking, the man in the house smokes, and the other thing is maybe a child puts on the electrical switch and causes an electric spark. Therefore, this is the way we are able to get a tree diagram for the final event in terms of the intermediate events and in terms of basic events through an AND gate, through two OR gates. Now, I want to calculate the probability of having an explosion. Let us say probability of the lady in the house forgetting to switch off is, let us say, P1. Probability of the cylinder being supplied with a faulty pressure regulator is P2. Then in this case, the probability of forming the combustible cloud is through OR gate P1 plus P2. And therefore, I come up to this, let us go to this. The probability of somebody smoking is, let us say, P3. The probability of having an electrical spark is P4. Therefore, the probability of having an energy release coming from both these things which are through OR gate is P3 plus P4. Now, I have these two intermediates. This has a probability P1 plus P2. Energy release has a probability P3 plus P4. This is through AND gate. Therefore, the probability of forming the final event, or which is the explosion, is equal to P1 plus P2 into I have P3 plus P4. Now, all I have to do is I want to calculate a net probability. If I know P1, P2, P3, P4, I can get my net value of the likelihood of a fire or an explosion. Therefore, let's put down some numbers. We'll try to see. See, normally when we do this, the probability for these things can be conjectured or can be taken from the large number of data which is available. The probability of somebody leaving the valve open, absent-mindedness, maybe tiredness, could be something like 0.0, 0.01. The probability, this is quite low because the pressure regulator, there are some standards to which the manufacturer has to associate. Maybe the gas people have to give better one, but still in some cases they do give faulty one. Let us say probability is 0.001. The probability of somebody smoking is quite large, let us say 0.1. the probability that the child finds something smelling and tries to switch on the switch and see what's wrong could be again, let us say 0.1. Therefore, the probability of having this is P1 plus P2, that is equal to 0.1 plus 0.1, 0.2 over here. The probability here is 0.01 plus 0.001, that is 0.011 over here. And when I multiply these two over here, P1 plus P2 into this, it gives me a net probability equal to 0.011 into 0.2, which is equal to 0.0022, and this is how we get the probability of getting an explosion from these values of probability. This is what we do in the case of a fault tree analysis. When we talk in terms of fault tree analysis, we find, well, basic events cannot be broken any further. If I keep on going further and further like this, if my length of my faults are progressively increased, then my final probability will probably come down, because each stage requires something, and if I can calculate something like a lot of processes involved, or if the final explosion involves a lot of faults, then probably my probability will be lower, 0.1. Second, the minimum set of these faults is what we call as a cut set, and if we can, from such type of examples, we can also find out which are those pockets or which are those gates or which are those basic events which have the largest value of probability and which lead to higher probability number, and we can focus on them to bring down the probability or the risk of having an explosion. This is what we do in the fault tree analysis. Having said that, let me take you through one more example which I show on the slide. Over here, I consider maybe a pipeline. We talked in terms of pipeline bursting. We said at propane, liquid propane, this happened at Port Hudson. We said in Siberia we had the gaseous methane line which gave way and there was a huge spill. And therefore, we are interested in finding out the final event is, let us say, a huge fire which results out. And how did the flammable mixture get formed? Well, in those cases it was essentially a weld failure. It is also possible that you could have a manual opening. You have at some places in the pipeline, you have, say, the gate valve or valves are there. Somebody might have opened it out. Therefore, your probability that a weld failure is P11. The probability that a manual opening takes place is P12. Well, both of them, either one of them can result in a flammable mixture. That means I go through the OR gate. You see the shape of the OR gate over here. The probability of forming a flammable mixture is P11 plus P12. Similarly, maybe along you have a gaseous cloud, somebody can walk with a cigarette in his hand and ignite the cloud, and this has been the case in case of most forest fires all over the country in different places. Well, cigarette seems to be a cause of majority of the fires. I could also have a car which travels next to the leakage line, and the friction spark because of the car tire hitting some stone or hitting the road or hitting some place creates a spark. The probability of having a cigarette burning is P21, P22. Therefore, the possibility of having an ignition stimulus is P21 plus P22 being a OR gate. And I need both these things. Therefore, I have an AND gate which communicates to my final fireball, and I have the probability being P11 plus P12 into P21 plus P22. That is the summation of these probabilities. The summation of these probabilities multiplied together is what gives me the final probability. And this is how we do the risk analysis for involving a fireball, an explosion. In other words, we try to go from top down through a deductive logic, come to the basic events and keep on progressing till a final explosion is formed. This is what we mean by a fault tree analysis. It is very successful. It has been applied for space, for being able to find out what are the defects which could lead to a loss of mission. Having said that, let us go to the next one, namely the event tree analysis. This is also something like a tree. But rather than using the deductive logic, which we used in the fault tree analysis, we use the inductive logic. What do we mean by inductive logic? What we do is we start from the basic event and proceed further till we get the final explosion. How do I do this? Let us again take a look at it. Let us say my basic event is over here, and I start from the basic event. I go to the next event. Maybe the basic event could either outcome could be, let us say, a successful event or an unsuccessful event, let us say. What is it I mean? Maybe I have a gas mixture, it either ignites or does not ignite, successful, non-successful. From this successful, I could have again another success over here, other non-success event over here. I could again have another success or non-success, I could again have another one, and so on till I have my final explosion. And therefore, I march from my basic event till the final event, which is an explosion, and this is what is done in an event tree analysis. For each of them, I could have a probability of this happening over here, this leads to this probability here, this probability leads to these two probabilities here, and I calculate my final value. Therefore, what is done in an event tree analysis is, let's try to put it down. I have, let me take an example, and nothing better than through examples we study. Let's take the example of an LNG in a pipeline catching fire and exploding. Therefore, let us say there is a leak in LNG pipeline conveying LNG. This is the basic event. Well, what happens is maybe the LNG leaks, forms a cloud, and the cloud either ignites or it does not ignite, no ignition. This is point 1. The gas that ignites could either explode, that means forms a strong blast wave, that means it explodes, something like a detonation. Well, it just forms a fire and burns out. Let us say that means it forms something like a fire or a flame. When it is no ignition, let us say it just disperses out. I will come back to this a little later, a more better example of even this dispersed gases can again create a havoc. Let's just now put down this. Therefore, we say, well, the final event is an explosion. Just to illustrate, this is the explosion. In this case, it burns out, no harm is done. Therefore, I want to calculate the probability of this. Therefore, I say the probability that an LNG pipeline coming out and ignites, hey, it's quite common. Maybe in summer month, I have a cloud, it definitely is going to find an ignition source. Let's say the probability is 0.08. The no ignition is the balance, 0.2 is the probability that it does not ignite. Well, it just disperses off. When it ignites, well, the possibility of having an explosion, if there are a lot of blockages like trees, buildings and all that, well, the probability is 0.5. Well, the probability of getting a flame is 0.5. Well, the probability of forming an explosion is 0.8 into 0.5, that is 0.4 is my probability of forming an explosion. In other words, we start from the basic event, go forward till we reach the explosion, and this is what we call as an event tree analysis. While in the fault tree analysis, we denote the basic events by circles and the intermediate events by rectangles and the final event by a rectangle. In case of the event tree, we show all by rectangles and just keep on multiplying the probability till we come to the final event. Let me take one example, a more strategic example, more illustrative example of having some more links in the event tree, and this I show in the slide over here. I am considering the case, since there is so much interest in hydrogen, supposing there is an hydrogen leak. The hydrogen leak comes out, there are two possibilities, either it finds an ignition source and gets ignited, the probability of this ignition is 0.55. It does not find an ignition source and therefore, it gets accumulated. Let us assume in this particular example that a cylinder of hydrogen is being carried through a tunnel, and this tunnel is a long tunnel, and therefore, in the tunnel the hydrogen leaks, like what happened at Stockholm in the downtown area. There was an hydrogen leak, and therefore, maybe it does not ignite, the hydrogen accumulates within the tunnel or within the space, and this accumulated hydrogen after some time finds an ignition source, and when it finds an ignition source, it could either explode or it could form a fire. But the accumulated hydrogen is more dangerous because it has had a lot of time for it to mix and prepare itself well, and when it burns in a confinement, well, it is generally going to explode rather than form a fire. Therefore, the probability of forming an explosion is 0.95, while forming a fire is lower at 0.05, or maybe this accumulated hydrogen does not really meet an ignition source, it just disperses. Well, the hydrogen leak which immediately ignites, well, it burns without an explosion, that means as a flame. The probability of this is higher because it immediately ignites, therefore, it just catches fire, and the probability of having an explosion is much smaller at 0.2. Therefore, you find in this case, if the hydrogen leak immediately ignited, the probability of forming an explosion is 0.55 into 0.2, which is equal to the net probability of an explosion is 0.55 into 0.2, which is 0.11, while if it forms an explosion here, well, no ignition probability is 0.45, and 0.45 into 0.95 gives me 0.4275. Therefore, this accumulated hydrogen is capable of having a higher probability of an explosion compared to the hydrogen leak which immediately ignites. Well, this is also a case of an event tree, you are going from base to this, but we do find, well, you should not really accumulate gases, especially in confined geometries or semi-unconfined geometries like let us say a tunnel or so, in which I would have an explosion. Getting back to something on another example involving hydrogen usage using fault tree is, maybe I could have a tankage of hydrogen having a defective valve, human error in opening the valve, forming a hydrogen air cloud whose probability through the OR gate is P1 plus P2 over here. I have an ignition source, it could be electrostatic spark, as we said smoking earlier. I could have probability here P21 plus P22, you have an AND gate, and the net probability of forming an explosion through the fault tree is this and this, and this is the basic difference between this example and an example having the event tree. Therefore, these are the two methods with which we evaluate the final probability of an explosion but more importantly, we also find while going through the paths, which are the paths which are more likely, and we try to plug in those things and ensure that the final event of an explosion does not take place. With this, let us come to the last part, namely the HAZOP analysis. And what is HAZOP analysis? Let us just put it on the board. We have hazards and operability analysis. Actually, this got started with chemical engineers in the Imperial Chemical Industries in UK, wherein they wanted to apply it for maybe making the plants more safe, namely the chemical plants. And therefore, what is done in this method is a little different. Let me take you through the discussions on the slide. In this, what is done is, maybe people sit through on a table, discuss what are the different things which can go wrong. But to be able to think and discuss, a suitable number of guide words are given with which they can stimulate their thinking and discuss on the different types of processes which are possible, which can lead to something going haywire, something which will cause a hazard. Therefore, to stimulate thinking and discussions on possible hazards at each step of the process are what is done, and what they do is for each of the process parameters or each of the processes, they say what are the process parameters, and what are the process parameters normally? Well, we talk of flow, so much mass flow rate or so much volume flow rate. We talk of temperature, we talk of pressure, we talk of concentration, we could talk of some other process parameters. For each of these process parameters, we use certain guide words to find out whether some of these, we want to find out whether some deviations in these process parameters and can result in something like a hazard, and for that let us take a look at guide words. That means at each step of the process we look at maybe the flow, the temperature, the pressure, the concentration using some guide words. And what are the guide words? Guide words are no, not, none, first guide word. Second guide word is more, higher, greater. Third guide word less or lower. Fourth guide word as well as. Fifth guide word part of. The sixth guide word reverse, and so on, different guide words. When I say no, not or none, what I mean is implying that there is no pressure. That means if I go back, the process parameters are there is no flow, there is no temperature, there is no pressure, there is no concentration. What would be the consequence? Similarly, if I say guide words more, higher or greater, what I mean is, well, the flow or the pressure becomes larger. When I say less or lower, well, the flow rate or the pressure or temperature becomes lower. When I say as well as, I mean qualitatively additional change is taking place. When I say part of, it means a qualitative decrease. When I say reverse, well, the flow takes place in the reverse direction. That is the opposite of what we want to do, or logical opposite. Therefore, using these guidelines and the process parameters, what is done is we try for each of the guide words find out, well, if the flow has to stop or if there is no flow, what are the possible causes which can lead to this? Maybe if there is no flow, what are the consequences which will be there? And if there is no flow, how do I correct for it? And keep listing out at each step of each of the sub processes, we keep doing this for each of the guide words, namely no flow, higher flow, less flow, maybe part of the flow, maybe less of the flow, maybe reverse of the flow, and so on. For each of the process parameters, you keep looking at the possible causes, possible consequences, and then based on all the listing which is made, maybe make a set of inferences then what can go wrong, how major would be the consequence, how often will it occur, that means the frequency of occurrence, and based on all the listing done, how to prevent its occurring. These are the inferences which are done based on the guide words as applied to the process parameters. Once this is done, we are interested in the consequences, we are interested in the likelihood of the explosion occurring or the frequency. Well, if you find that the consequence is severe, that means based on the guide word, based on the different process parameters, if we find that the consequence is severe, we say it is category 1. If the consequence is medium, we say it is category 2. If the consequence is very low or something like not medium but low side of medium, we say category 3. And if the consequence is very low, that means hardly any consequence, we say category 4. So also when we see the likelihood of occurring of the explosion or likelihood of occurring of the final event which is undesirable, that means likelihood is something like frequency. We can also catalog the frequency as being category 1 when the frequency is large, when the frequency is medium, category 2, when the frequency is low medium, we say category 3, and then the frequency is low as category 4. Therefore, these consequences and the frequency are put together in the form of a hazards and operability risk rating procedure, wherein both the consequences and frequency are put together to get the net risk rating as either A, B, C or D categories. And how do we do this? Well, we say consequence 1 is most severe, and if the frequency is also very severe, we give it the grading D, which is a grading which is a bad grading, the risk is very high, well, I should not go ahead with it. If the consequence is, let us say, medium low, and if I say, well, the frequency is still higher, that means the frequency of occurrence is still very high, but the consequence still I give the grading low, because well, the frequency is going to occur even though the consequence is less, I still have the problem. If my consequence is low, medium low, and if the frequency is still high, well, I cannot operate it because my plant is going to be always shut down because the frequency of occurrence is very large. But if my frequency of occurrence is, let's say, if my consequence is somewhat very low and the frequency is higher, maybe I could still tolerate it, because it may just result in minor shutdowns and I can do it. Therefore, according to the consequence, and let's take maybe consequence 1, if consequence is very high but the frequency is, let's say, very low, you still have a high value of B, because the value, the B is something which is acceptable. Once in a way you have a high consequence, but this is something which is not very desirable, because if I have something like a Bhopal gas tragedy which happens once in a lifetime, well, the consequences are very bad. Therefore, B is something which can be acceptable risk, that means it is as low as reasonably practical, it is category B, but we have to take some steps such that we make some checks and balances such that we tend to operate a plant when it is under category B, but we make sure we do some checks on it. When the others are all in between, when I say that the frequency is very low at 4, consequence is very low at 4, well, there is no issue at all. This is a safe, that is, there is no risk involved. When I say risk C is undesirable risk, maybe I have to improve my plant operation. If I say risk is D, well, it is a risk in which it is not worth undertaking. This risk is not to be pursued on. You must improve the plant to either B or preferably to A. B is acceptable risk, and as I said earlier, as low as reasonably practical, and this is category B. We put all these different categories in the form of a plot in HAZOP, that is the hazard and operability analysis, and what we have is, I show the consequences here, the frequency over here, and what I find is, if the consequences are very large, well, the thing is, if consequences are very large but the frequency is very small, then maybe after some checks I still have to accept it. If my frequency is very large but the damage is or the consequence is very small, well, I have to accept it. This is the region in which I have acceptability, that is region B over region C. Region B is what we said earlier. We said acceptable is B. We have region B over here, and this is the region C and D, which is not really acceptable. Therefore, the HAZOP plot gives the acceptable range of consequences and frequency, and this is what is done in HAZOP analysis, namely you evaluate the consequences, you evaluate the frequencies and put everything together in terms of A, B, C and D categories, and evaluate the risk in these 4 categories, and this is what is done in HAZOP analysis. But we must remember that the HAZOP analysis is carried out maybe even before the plant gets commissioned. During the design phase itself, we sit on each of the processes in the plant and make sure that no untoward thing is possible. Each and every element in the plant is considered, and also maybe provision of alarms, automatic shutdown, automatic starting, provision of relief valves, etc. are considered while doing the HAZOP analysis, and this is the third type of analysis, namely HAZOP analysis. Therefore, to summarize, we in this class have done something on risk analysis, evaluating the risk through 3 methods, namely the fault tree analysis, second the event tree analysis, and thirdly the HAZOP analysis. And these things give a good picture on what is the final probability of an explosion taking place, what are the safety features to be put in. But while talking on safety features, something which we have to keep in mind is, we have to keep in mind whenever we talk of explosions, of the explosion triangle, maybe fuel, maybe an oxidizer, maybe an ignition source. We talked in terms of inerting, we talked in terms of critical diameter, we talked in terms of maximum safe operating gap, such that an explosion does not occur and does not get transmitted to something else. But when we talk of ignition, it is possible to inert, it is possible to vent out the gases, it is possible to build in the safety features. But when we talk of ignition sources, especially when we talk of electrostatic sparks, it is possible, I work in an environment, I walk, the human body can get charged to a voltage of 25 kb, and maybe my body, when it is charged and I touch something, it can also create an electrostatic spark. Therefore, from safety point of view, maybe if I can wear something like on my wrist, a chain which is on the ground which conducts away the charge, or I have something like a wrist stat or something like a leg stat. On my leg I have a chain which is in contact with the ground and it gets grounded and no spark is formed. Well, I can avoid electrostatic sparks, but we also can remember that if I have a room and if it is more humid, electrostatic sparks are more unlikely, and therefore we must devise means by which I can isolate an ignition source from the combustible mixture, and even the combustible mixture by suitable inerting, or when I have an explosion taking place, by suitably venting out, I can decrease the degree of the consequences of an explosion. Therefore, this is all about the course on introduction to explosion and explosion safety. We covered the different aspects, including the safety aspects, the consequences, the reasons for causing an explosion, and how to go about preventing an explosion. Well, thank you. Announcement, please. The last set of lectures between lecture numbers 33 to 40 covered condensed explosives, the TNT equivalence of explosives and their yield, atmospheric dispersion, quantification of damages, and risk analysis. Further references on these topics and a few homework problems are given in the downloads of this video course.